So I'll talk about an application of linear algebra in TCS, but in particular graph theory. So I'll start with a data communication problem that arose at Bell Labs. It was formulated as a graph theoretic problem. We'll see a formulation of it, and Graham and Pollock they proved a theorem about this graph problem, and we'll see two linear algebraic proofs of it, even though the statement of this theorem is graph theoretic. And finally, I'll talk about some open problems and also some solved problems that if you find this interesting, you could read more about, right. So here is this data communication problem. So imagine a network. The nodes are computers, wires are edges, and you can think of it as a game. In every round, we'll label a vertex or a computer as source or a target or dormant node, and messages travel from only source node to the target nodes over multiple rounds. So no messages between two sources and no messages between two targets. The goal is that we, with minimum number of rounds, we want to send and receive message over every wire with the condition that every wire is used only once. So let's see a round of this game. So in the first round, let's call these two set of vertices as sources, these two as targets, pass the messages. So note that there won't be any message transfer between two sources and two targets, and all sources communicate with all targets. So let's bring this substructure out. So here this is how it looks like. I'll use rectangles for sources and circles for targets, and solid circles for dormant vertices. In the next round, so all these blue edges are now used. So with the condition that wires are used only once, they won't be used in subsequent rounds to send messages. So in the next round, let's make another vertex a source and pass messages. Let me write this transcript here. Then in the third round, only two edges are remaining now. So either pick one edge, make one endpoint source, another target, and pass message, and so on. For the last edge, do the likewise. So this was how a run of the game looked like, and the problem here is that what is the minimum number of rounds that you need to cover or partition all the edges. So what this looks like below is a partition of edges of the complete graph. If you have seen complete graphs, because we modeled the computer network as a complete graph. So what are these graphs below? Can you recognize what type of graphs are these? Bipartite, but more particularly, more specifically, these are complete because the condition was that all sources communicate with all targets. So there won't be any edge between two rectangles, there won't be any edge between two circles, and all the sources are adjacent to all the targets. So what this problem is basically is partitioning this graph, edges of this graph, using complete bipartite graphs. So every edge of this graph must appear in exactly one of these complete bipartite graphs. So what I described to you is a version of a original problem. The original problem was called loop switching problem. So it was described in a completely different language. What Graham and Pollock did was formulate that problem as a graph theoretic problem, but although that problem was also different, they wanted to label a graph so that messages know how to go from one end to another end very efficiently. At that time, the distance between two nodes depend the cost of the. So if you assume telecommunication network, so the cost of a call depended on the distance between two nodes. So they wanted to optimize this cost. So you are free to look at this paper and read what was the original problem, but in this talk I'll mostly just restrict to graph theoretic formulation. So yeah, so just to make remind some definitions. A graph will consider the vertices of a graph labeled. We'll label it from 1 to n. Edges will be subset of V cross V, and this will be an unordered undirected graph, or edges will be unordered. Whether we consider AB or BA will be the same. So in this complete graph, the set of edges is basically set of all pairs where A is less than B. Similarly, there is a bipartite graph which is a tuple. What you do is partition the vertex set into two sets L and R, which are disjoint, and edges are only across L and R. So this is also called a biclic. We'll denote it by K PQ if. So these two sets L and R, we'll call it partite sets. If their sizes are P and Q, we'll call it K PQ, K sub PQ. And here the edges of this complete bipartite graph is this Cartesian product L cross R. So all the pairs where first coordinate is from L, second is from R. So this is the formal statement. It's called biclic partition problem. What we want to do is partition edges of the complete graph using edge disjoint biclics. So biclics are complete bipartite graphs, and what we want to do is find out minimum number of biclics that are required to do this job. This is also thought of as a jigsaw puzzle where your big picture is a complete graph and pieces are biclics. These problems are very general, like in general partitioning or covering. So pieces could be various other subgraphs, and this big picture could be any arbitrary graph as well. So we'll see just this restricted setup of the problem. So what is the trivial solution? Like, what is the trivial upper bound on this number? I told you a run of the game, but what do you think should be the trivial solution? Can you estimate B of Kn, the number of biclics required? Number of edges, yeah. So treat each edge as K11. Every edge can be thought of as complete a biclic basically, and that's an upper bound NC2. Number of edges in complete graph is NC2. We want to do better than this, obviously. So can you do better than NC2? Yeah.
Take one vertex, pick star.
Yeah. So basically take stars. So stars are basically complete bipartite graphs where one of the partite set is a singleton set. So for example, K14, first partite set is singleton. So what you do is pick any vertex, call it a source, rest of them targets, take this graph. Then now all the edges adjacent to this vertex are covered, like they won't appear again in another biclic, right? So that will be dormant. So take another vertex, take the star corresponding to it, and so on. So how many are enough?
How it is equivalent to a problem that you are partitioning?
So what you see before is, you can also think of this as that game where in the first round you call this source, rest of them targets, and yeah, I have to decide. So the problem is, what is the minimum number of rounds? The way you do it is up to you, right? So what is the number we get upper bound on B of Kn if we follow this star strategy? N minus, right? And now, is it optimal? Is this sort of strategy to find B of Kn, like, is it equal to n minus 1 or can we do better than n minus 1? So that's the question. So what Graham and Pollack did was they showed it's optimal. If you can cover a complete graph using edge disjoint biclics, the number of them should be at least n minus 1. and this is the main theorem that I want to talk about. An interesting thing about this theorem is that um, all proofs somehow use linear algebra, and there are also various formulation of this. I told you one about this communication problem. The original was labeling a graph so that something is optimized. I'll also tell you, so I'm going to give you two proofs and come up with two other ways to look at this problem, right. There are of course many other proofs, like but somehow all of them use linear algebra. So the original proof was based on eigenvalues of matrices if you associate matrices with this graph. The Sylvester law of inertia basically says that if you have a matrix and you take some sort of transformation, the number of positive, negative and 0 eigenvalues are preserved, the number of them at least. So that was the original proof was based on that idea. There is also something called binary rank. There is a proof based on that. I will come to this binary rank later. And there is a proof based on setting of system of equations and trying to give a proof by contradiction, saying if there is a solution that gives you contradiction. There is a proof based on polynomial space method. So essentially the idea is you look at space of polynomials as a vector space, and Vishwanathan, he gave a proof where he tries to replace the linear algebra part of the proof using counting argument. So there is also a question. So this was in 2013, and these two people said there is no combinatorial proof. So if you explain linear algebra using counting argument, do you think that is a combinatorial proof or a linear algebraic proof? So suppose there is a linear algebraic theorem, statement. If you give a combinatorial proof, is that linear algebraic proof or a combinatorial proof? So that's up to discussion. So even though he tries to explain the linear algebra using combinatorics, it's a translation, but whether you want to call it combinatorics or linear algebra is up to debate. So what we'll see is a proof based on rank argument. Like my proof is adaptation of some of the ideas that have appeared before, and one based on setting system of equations. So any question about the problem that we are doing so far? And this particular problem, bi-click partitioning, has appeared in many places, but partitioning and covering are very general problem. So that's one thing I wanted to mention. So any question about the problem we are working on? Yeah, so let's see, I'll start with the rank based proof. So I have to define a matrix first whose rank I want to talk about. So this is an auxiliary definition. There is no, I don't think anyone has defined partial adjacency matrix as it is. So I'm just giving it a name. So is going to be a upper triangular matrix. So you might have seen adjacency matrix is something similar to it. The only difference is that if there is an edge between I and j, you put ijth entry to be 1, but not the jith entry. Jith entry will be 0. So it's going to be upper triangular matrix, assuming that your vertices are labeled from 1 to n. So all the entries of this matrix will be above the diagonal. So if you add the transpose of this matrix to itself, you will get the usual adjacency matrix, which is symmetric. So I talked about two graphs, so let's just look at rank of those two graphs. So here is a complete graph, and correspondingly the partial adjacency matrix looks like this. So what's the rank of this matrix? In general, if I have kn, n minus 1, because the first n minus 1 rows are linearly independent. So that's one observation that we need. We talked about complete bipartite graph. So if I label the vertices, so first the vertices from L and then R. So first block will be 0, the third and fourth block will be 0 because of the definition. What's the rank of this matrix? 1. because all the other rows are so much first. So that's these two only things we need. So yeah, so let's call B of Kn the bicyclic partition number as T. Let's consider some minimal bicyclic partition H1 up to Ht where T is B of Kn. And it should satisfy two conditions. That first is that all the edges of these bicyclics should be disjoint. The second is their union should be all of E of Kn, right? So let's fix some ordering of vertices. Let B1 up to Bt be the corresponding the partial adjacency matrices. Even though these bicyclics might be on lesser number of vertices than n, I am going to define n cross n matrix so that I fix the ordering. If there's a vertex which is not in Bi, then I'll put 0 row and 0 column correspondingly. So first observation is that this partial adjacency matrix of the bicyclic is entry wise at most U, where U is, let's say, the partial adjacency matrix of the complete bipartite, complete graph, right? So this is fine, this observation. Bi will be at most U entry wise, because every edge of Bi appears in U, appears in Kn, right? If this is fine, then another observation is that because all the edges between bicyclics are disjoint, edge appears in exactly one bicyclic, the sum of them should also be at most U. That's based on this disjoint property. Yeah, it's equal to base because of the union property. So this is fine, right? The bijection between entries of the matrix and edges in the graph. Let's take rank on both sides, and there is this property that rank satisfies, that sum of rank of sum of matrices is at most sum of rank of the matrices, and this proves your theorem. This is the most simple proof, that all these Bi's had rank 1 we saw, U has rank n minus 1. So so why this proof was interesting was because we could come up with, we could see bicyclic partition number in a different through a different definition, that you could also convince that this number is also same as minimum number T, where your partial adjacency matrix of complete graph can be expressed as sum of T many 0 1 matrices of rank 1. And if you drop this 0 1 condition for the rank 1 matrices, what you get is the usual notion of rank. That's, if you don't know that, that's an exercise you should try to convince, that if you drop the 0 1 condition, what you get is the definition of the rank, that a matrix has rank R if you can write it as sum of R rank 1 matrices, and R is the minimal. So this was what was going on in this proof, and what this definition is called is binary rank of a 0 1 matrices. So you define rank for real matrices. Similarly, for 0 1 matrices you define binary rank, and that was the sort of equivalence, that bicyclic partition number is same as binary rank of the partial adjacency matrix. Here you can also see a reduction sort of, if you want to compute bicyclic partition number, you should compute binary rank as well. So there is sort of reduction. So if this one problem was hard, another will also be hard. So so let's move to second proof. But any question about this proof so far? It's very simple, but is there any doubt that why it's simple?
Can you do this without partial adjacency?
Yeah, there are many proofs. So here I just took partial adjacency matrix, but people have worked with just this equation as well. They tried to argue based on contradiction. I just separated it out, like just took U out. Yeah. So from the second proof, you'll also derive some equivalent definition of the bicyclic partition number. So let's start. So same as before, E is the disjoint union of edges of this minimal biclic partition. You can also write this as this. So the left hand side is the edges of the complete graph. That's just set of all pairs where A is less than B. On the right side you have pairs where A is in Li, B is in Ri. Let Li and Ri be the parted sets of these biclics H1 up to Ht. And if we associate some variable xi with each vertex, this is same as saying this, where left hand side, so it's a polynomial, like we are trying to encode this information into polynomial equation. So left hand side is sum over all the edges of the complete graph. So I've written xa xb, and xa xb, this term appears only once in the summation, it does not repeat. On the right side I have sum over all these biclics, and I am summing over the same thing for that biclic. So this is encoding the information, this information in equality into polynomials, right. But I mentioned proof is using linear equation, but this looks like this looks non-linear. So we want to extract out some linear equations. So here is the idea of the proof. We will assume we want to prove t is at least n minus 1. So assume on the contrary t is strictly less than n minus 1. So that's saying t plus 1 is less than n. Number of variables is n. The idea is we will define system of t plus 1 linear equations, and because the number of equations is strictly less than number of variables, this will have a non-trivial solution. So if you have system of equations, you can think of it as matrix vector equation, right. But if this holds, then your nullity is at least 1. So other than 0 solution, there are infinitely many non-zero solutions. So what we want is that it has non-trivial solution. So let's write extract these linear equations from this above equation. So let's recall the first the left hand side appears in this equation. If you take square of sum of variables, this term appears there. If we remove the sum of squares here, so let's add it to the left hand side. Replace this term with this term, and this is trivially because of this sort of disjointness between Li and Ri, were parted sets of a bipartite graph. So Li and Ri are disjoint, so you can separate them out. So now everything looks linear, like this is linear, this is linear, this thing is also linear, but not this. So let's also write this here. So we have found 3 linear equations, this one, this one, this one, this one, and this one. So what I wanted to do was define t plus 1 linear equations, right. So let me define them to be these linear equations. So sum of xa, where a goes over all the numbers 1 to n, and here the sum is over all numbers from Li. Now because these are t plus 1 equations, n variables, because of our assumption it will have non-trivial solution. If we plug this thing here, sum of squares is 0, that's equivalent to saying this x is 0. So that's a contradiction because we started with a non-trivial solution. This is another simple proof, and this proof is there on Wikipedia if you want to look at. So here the idea was recognizing that you can encode the information about the biclic partition in terms of this equation, and what we did at the end was sort of wrote the left hand side as a sum of product of sums, and it turns out that biclic partition number is also the minimum number, such that this LHS can be written as sum of t many product of sums. So, these are called linear forms here, where if this sum is over Li, this is over Ri, those sets must be disjoint for all I. So, the second proof gave us different way of looking at biclic partition number, and yeah. So, that's so yeah. So, these were about the proofs. So, any questions so far about proofs that you have? Yeah. So here is my second last slide. My talk is almost over. I just want to leave you with some problems that you could think about. So first is obviously all proofs are somehow based on linear algebra. Could you give a purely combinatorial proof? If you are the person who is just happy with any proof, one proof is enough. Then there are many other problems you could think of. But personally, I find that there is no purely combinatorial proof, and why is it difficult to come up with purely combinatorial proof? That's an interesting question. We saw we could come up with a partition of size n minus 1, that's also optimal. The question is how many different biclic partitions are possible. This is an exercise in some textbooks, so I think you should be able to do the second problem. And I also think like you might want to check whether answer to the second question says anything about the first problem. That's up to you to check. So when Graham and Pollock proved this theorem for a complete graph, they also computed this number for trees and cycle and other kinds of graph, but they couldn't find an example of a graph for which this number was n. So they conjectured it must be true for all the graphs, all connected graphs. And Graham offered $100 for someone who will prove it or give a counter example. So a lot of people tried it and they couldn't prove it. Then he raised the price to $200, and then Winkler proved it. He won $250 instead of 200, I suppose. And later Winkler says this was his biggest break, that solving this conjecture that biclic partition number was n minus 1, and eventually he also got a job in Bell Labs because proving this conjecture. It was known as squash cube conjecture because of the equivalence of this problem as a problem where you want to find an embedding of a graph into what is called squash cube, and you wanted to minimize the dimension. So that's another equivalent way of seeing biclic partition number. And I would, this theorem is there in West book, like the graph theory book, so you could check out that book. Yeah. Then Babai Frankel defined, they asked for a odd cover problem. So in partitioning, edge must appear in exactly one biclic. In covering, you can relax that condition. In odd cover problem, you can say an edge can appear in only odd number of biclics. So this problem was addressed by Radhakrishnan, Sen and Vishwanathan. Their approach to this problem is circuit complexity theoretic, like site, and it starts with this definition, of looking at it. What you could do is, what you want to do is compute these compute this left hand side, which is called a symmetric polynomial, if you know, using arithmetic circuits. And here the problem is minimizing this t, so that you could so if you were to write, so I'll just mention this and not give a diagram, but if you want to compute this using arithmetic circuits, what you need, you need a circuit of size n square, but if you use this formulation, you need a circuit which is just linear in t, but we saw t was n minus 1 for a complete graph, so it's an improvement from n square to n. So if you are interested, you can check out this paper where they talk about this kind of approach to this problem. And in general, in network sciences, covering partitioning problems are there. What is a template? Is just a set of subgraphs using which you want to cover or partition the graph. So, if you are given network, you want to find some meaningful communities using dense subgraphs. So, that is a general problem. And of course, you could also talk about algorithms. If you solve this problem, you will get $1 million if you find an efficient algorithm. Here Chandran and people, they gave an algorithm that uses this binary rank definition, and their algorithm also uses the linear algebra of approach to bi-click partition. And so I think their algorithm is the best one. I think it's around, I don't know, there is a pen. So their algorithm is like 2 raised to, so what is the decision problem? Pen is here. So your input is a graph and you are given some parameter. Your question is bi-click partition number of this graph at most k. So this is the decision problem one could think about. And they gave I think 2 raised to order k square n raised to order. And I think this is also the best algorithm. It uses linear algebra, so it would also be interesting to do it without linear algebra if someone is interested. Interesting thing is that this Davis Isaac was a PhD student at ISC with Sunil Chandran. This was his PhD thesis, graph covering and partitioning problems. There is this Uber-Wolfach problem. Wikipedia says this is unsolved problem in mathematics, and here basically you want to partition the complete graph using only copies of a fixed graph G, not any bi-click, and that fixed graph G is any two regular graph. What are two regular graphs?
Every vertex has a degree to.
Yeah, but what are the graphs? No, disjoint cycles. Yeah. So you want to partition the complete graph using G, where G is disjoint union of cycles. And this problem had appeared in some conference around this time. What they wanted to do is find a seating arrangement of mathematicians around round table, so that something happens, like everyone gets to meet each other or something. So if you see Wikipedia, this says this problem is almost solved except for only 4 cases. You are welcome to check out those 4 cases and think about this from partitioning problem. Yeah. So finally, I'll just mention this book that I'll recommend you to look at this book for more applications of linear algebra. The Graham-Pollock theorem proof is there in this book as well. The proof is slightly different, and there might be many other problems that you have seen before in last 2-3 days that you will see here as well. In particular, how to test for a triangle in a graph using matrix multiplication, or find perfect matching using polynomial testing. And the first 2 chapters is like computing Fibonacci numbers using matrix multiplication. So yeah, that's all I wanted to talk about.